Today we are here to talk about Apache Pulsar in Yahoo or Verizon Media. Throughout the talk, I will use Yahoo and Verizon Media name interchangeably. We'll talk about Pulsar, how Pulsar has been developed here, grew and scaled over the years with different use cases and with the different tenants in a shared cluster. Onboarding and serving these different use cases from different tenants on a shared cluster always bring the challenges, such as like performance, scaling, data isolation, noisy neighbor, security, privacy, and many more. So we'll talk about how do we use Apache Pulsar to handle such multi-tenancy and the security challenges in Yahoo in a multi-tenant environment. So let's start with a Pulsar overview in Yahoo. This slide shows a glimpse of Pulsar's journey in Yahoo. We have started building and using Pulsar in 2014 and then open sourced it 2016. Pulsar is operated as a hosted service in a private cloud within Yahoo, and it is deployed across 6 different data centers in the world. We fully replicate across all of them with full mesh. Pulsar is backing, a lot of business critical use cases within Yahoo. Uh, Pulsar is an extremely scalable and low latency system, and other low latency systems are actually built on top of Pulsar for their messaging use case in the Yahoo. So now let's see how large-scale system requires multi-tenancy feature to give seamless experience to every tenant on a shared cluster. So last year we gave a detailed presentation about how we scaled up Pulsar to manage, high throughput with low latency in Yahoo. We had described there several reasons why Apache Pulsar is an enterprise-grade messaging solution that you should consider for your high throughput real-time business use cases. However, in multi-tenant applications, tenants usually share the same computing resources and will eventually come across the situation where one tenant starts consuming more resources, and that can sacrifice the performance for the other tenants. And in Yahoo, over the time, with more number of tenants and the scale, Pulsar also evolved with various type of storage and its presence in various deployment environment, such as like on-prem, public cloud, or even Pulse integration with cross enterprise messaging bus. So it shows that Pulsar very well handles scales with the user growth and traffic. But what about the multi-tenancy and the security aspects? So before we talk about multi-tenancy and security challenges of Pulsar in Yahoo, let's see overall usage of Pulsar as a messaging bus in Yahoo. So this diagram shows how our users securely access Pulsar from different regions, different cloud environment, and even different organizations for their messaging use case. The left side of the diagram that shows we use the Pulsar Proxy solutions to allow our users to securely access on-prem Pulsar from public cloud or different enterprise or the cross organizations. The right side of the diagram shows various multi-tenancy aspects such as hard isolation, soft isolation, encryption, authentication, etc. We'll discuss each of them in details in the next further slides. So in this presentation, we'll talk about some of the key aspects about multi-tenancy and security. Apache Pulsar as an enterprise messaging hub has supported multi-tenancy from the day one. And that's because, it was needed to serve the demanding requirements of Yahoo use cases. For example, we need to make sure like we are providing the strict SLAs in terms of the latency throughput. We guaranteed isolation between the tenants, enforcing resource utilization quotas, and for sure, we need to provide per tenant and the system-wide various securities. So we'll try to understand each of these metrics in the details. So let's start with multi-tenancy. And for that, I would like to invite Ludwig to talk about, what are the different Pulsar features we use in Pulsar to manage the multi-tenancy.
Thanks. Although I'm still seeing the very first slide, Rajan, I'm not seeing you advancing slides. Are you seeing your current slide in this in the event view?
I am. I see tenant and namespace as the current slide, and I've been seeing them move forward.
Okay, that's strange. All right. Well, I have.
So I'm on the slide 9. Yeah, I'm on slide number 9.
Okay. All right. Well, I can talk. All right. So I'll just tell you when to advance then. Okay. So Pulsar, as Rajan mentioned, Pulsar was designed with multi-tenancy in mind, since the reason for its creation was meant to serve as a company-wide hub sub messaging platform. Some of the multi-tenant features I'll describe are obviously a fundamental part of the platform, and others were added on as we found some tenants being inconsiderate to their neighbors, for example. So the hierarchical topic naming scheme shows the assumption of a multi-tenant environment. You can see from the topic name already, like the tenant which owns every topic. Let's see. One of the necessary features for the sanity of the platform's operators of a multi-tenant system is the delegation of management operations to those tenants. But you only want to delegate those things which are safe to do so, which I'll touch in a later slide. So we provide tenants identified by their tenant name and managed by one or more authorization principles by which they can identify themselves. And we provision them with also a list of clusters in which they're allowed to create namespaces. We as operators manage the tenant data, and usually a tenant, being like one team, for example, they manage their own data and their own data policies, which will be flowing through their namespaces. Namespaces, on the other hand, are created and managed by tenants, and that gives them the highest level grouping for managing their data policies, as I mentioned. So they can manage things like in which clusters their namespace runs, the retention policy, the time to live, and the backlog quota policy. So those are namespace policy. There are namespace policies which the tenants aren't allowed to manage because they're really best left with the cluster operators. Things like throttling, the persistence policies, and the bookie affinity groups. So those are things which are too low level for tenants, and also things that they shouldn't be held responsible for understanding. Slide 10, please. So as one of Rajan's slides show, we have over 120 tenants provisioned in our production environment. Even though tenant management is supposed to be done by the Pulsar operators, we don't really want to be the bottleneck for common operations, nor do we want to take on all the trivial tasks of tenant management. So we have a self-service tenant provisioning and management portal. In our Pulsar instance, tenants are associated with a product or a platform team. When a user logs into the portal, it determines the user's team and shows them their team's tenants, of which they can have multiple, or lets them create a new tenant belonging to that team. If their capacity ask is below a threshold and we have enough cluster capacity available, the tenant is automatically created. If their ask is too large, the portal creates a JIRA ticket for us as operators to review. If the tenant wants to do something simple like just changing their admin authorization principles, the portal lets them change that. And the portal is what calls the Pulsar admin API to manage the tenants for creating tenants or just modifying the admin authorization principles list. Slide 11, please. So multi-tenancy, because multi-tenancy was such a fundamental requirement to Pulsar, it was a factor in designing pretty much everything from the beginning, including the IO paths and the messaging model. So both JMS and or ActiveMQ specifically and Kafka taught us you don't want anything the consumer is doing to be able to impact the producer. Similarly, you don't want what one consumer group is doing to be able to impact another one. They could be totally separate teams with different levels of support. IO isolation in Bookkeeper means that the producer can keep publishing messages no matter what the consumers are doing, whether the consumers are doing tail reads or backlog reads. Tail reads are served out of the broker or the bookkeeper cache, and backlog reads are read from the bookkeeper data device, also known as the ledger device. Publishes just need to make it to the journal, and then for the journal device to sync to the data device, and that's achieved by batching of writes and prioritizing flushing those writes over serving backlog reads. Multi-tenancy also came into play in the messaging model and supporting different tenants producing and consuming. the producers just publish messages to a topic, and the consumers, based on the subscription mode, can consume it in different ways. Unlike in JMS, for example, the producer doesn't have to know or care whether the consumers are going to be consuming as a shared queue or as an ordered topic. And we supported multiple tenants also consuming from the same topics or namespaces by delegating permission management to the topic's tenant, including granting permission to specific subscription names by authentication principle, allowing different consumers to consume from a topic without risk that they will stomp on each other's subscriptions. Slide 12, please. So storage quotas and throttling are what we think of as soft isolation. We use application level controls to limit the usage of resources by tenants while still sharing those resources. Storage quota is a tenant-controlled resource because it's really intended to prevent runaway producers or abandoned consumers from causing too much trouble for the application. Storage quotas aren't generally going to prevent a tenant from using up all available storage on a cluster, since they can just create more topics and use up all available storage that way. The storage quota policy is also important for the isolation of effect between producers and consumers, as you generally need the consumer eviction policy, so you don't want an abandoned or misbehaving consumer to impact the ability of the producer to publish to a topic. You can see there are a number of throttling dials. These are really just intended to limit the shared broker resources a tenant can use. As we have seen, for example, a newly implemented tenant who created a producer for every message published, resulting in brokers running out of memory from hundreds of thousands of producer objects, or consuming backlog messages so fast that the JVM's garbage collector couldn't keep up. Slide 13, please. Broker isolation is one of two methods of what we think of as hard isolation. We sometimes isolate tenants onto separate brokers to ensure there's very little one tenant can do to another, at the cost of reduced cluster efficiency due to carving up shared broker resources. The advantages of broker isolation over creating whole separate clusters is you still get to share the bookkeeper and zookeeper clusters, and changing isolation policies is very cheap and fast. With one admin call followed by a namespace unload or a broker restart, the new isolation policy takes effect. So that takes just seconds. Slide 14, please. Bookkeeper isolation is the second method of hard isolation. So Bookkeeper is generally a well-behaved system and quite resilient, and it's not easy for one tenant to impact another. But Bookkeeper also doesn't lend itself well to heterogeneous server configurations. If you have tenants with significantly different storage or performance requirements, it makes sense to put one server configuration into one Bookkeeper affinity group and the other configuration into a different group, and then assign namespaces or brokers to those affinity groups. And just like with broker isolation, you can move tenants between different affinity groups with an admin call impacting the namespace policy, and then a broker restart or a namespace unload. Slide 15, please. Something that one of our tenants requested, and that you do see in systems like OpenStack, for example, is anti-affinity groups. So the tenant requested a minimizing of an impact from server or rack failures. So that required us to implement two features which go hand in hand: failure domains and anti-affinity groups. So failure domains are a way of defining a group of brokers which are at risk of failing together. You could use a physical rack or an availability zone as your unit of failure, for example. If you don't have anything larger than the broker itself, then the broker becomes the unit of failure domain. So defining a failure domain on its own won't change the behavior of the system, but it does work in conjunction with the next feature. 16, please. So to support the request to minimize the impact from a server or rack failure, we have anti-affinity groups. And although it's true that a load balancer will automatically reassign namespaces when brokers go offline, you still have to wait for 30 seconds or however long your zookeeper session time is before that starts happening. Also, you don't really have any assurance about the proportion of effect or proportion of unavailability of your namespaces relative to how many brokers went offline. Due to the due to the load balancer policy and just the load on your other brokers, you could have the majority of some one tenant's namespaces on a small subset of brokers, which are all impacted together. But with anti-affinity groups, the load balancer will evenly distribute the namespaces in a given anti-affinity group among the failure domains, or just among the brokers if you have no failure domains defined. So for example, if you have 5 brokers and 4 namespaces, you will be guaranteed that each broker will have no more than 1 namespace in it, and a broker failure will impact 0 or 1 namespaces. That's it. Next slide.
All right. So thank you, Ludwig. Now we'll talk about various security concerns and how Pulsar fulfills all of them. We use Apache Pulsar and Yahoo to stream and store critical data, which makes it one of the most critical components of a company's data infrastructure. Our goal is to make it possible to run Pulsar as a central platform for streaming data and supporting anything from single application to whole company. Multi-tenancy is definitely an essential requirement in achieving this vision, but security features are also a crucial, for this kind of multi-tenant environments. So let's start with authentication and authorization. Authentication and authorizations are basic stepping stones for the security. Pulsar supports a pluggable authentication mechanism that client can use to authenticate themselves. Currently, Pulsar supports different authentication providers and allows us to use more than one authentication provider at a time. Pulsar is shipped with few inbuilt authentication providers, such as TLS authentication provider, which also enables encryption over the wire. Pulsar also supports Athens authentication, which is role-based authentication framework and open sourced by Yahoo. Along with TLS and Athens, Pulsar also supports Kerberos and JSON web token authentication, which is kind of proposed internet standard solution for authentication nowadays. So now once Pulsar authenticates user request using one of these authentication provider, it extracts the principal role name from the authentication process. Once Pulsar has the principal role name, it can authorize this role to check if it has the permission to access the topic or not, which is nothing but the authorization. Pulsar also supports pluggable authorization mechanism, and it's also shipped with the default implementation provider, which stores ACLs for the topic or the namespace into the zookeeper. So Pulsar provides various options for authentication and authorizations. And as we discussed, Pulsar provides end-to-end TLS authentication support between client and the broker communication, and even between broker to bookkeeper communication. So let's check how does Pulsar provide end-to-end encryption over the wire when the client publishes or the consuming the messages. As we already know that full in-flight encryption is often a requirement for the data security in any big enterprise. So Pulsar allows us to configure all communication with TLS, and which is the a common cryptographic protocol that provides data encryption as it is transported across the network, and therefore it is also known as encryption over the wire. It allows clients to connect to the broker using their own TLS certificates, and and then broker can authenticate. Clients, the certificate management and key store generation is kind of out of the scope of the Pulsar, and that should be taken care by clients separately. But these are the standard TLS practice. However, Pulsar user can provide file path for pre-generated TLS certificates, or user can also provide custom provider to read the certificates from the stream if the certificates are generated or fetched dynamically from the KMS. So along with TLS authentication, Pulsar client library also supports hostname verification. So during an SSL handshake, hostname verification establishes that the hostname in the URL that actually matches with the hostname in the server's identification. And this verification is necessary to prevent man-in-the-middle attacks. So this diagram shows how do we use TLS authentication between every component in the system. We enable TLS authentication between client and broker, between two brokers for the geo-replication, and between broker to bookkeeper when broker talks to bookkeeper to persist the data. We also use TLS for other components such as Pulsar Proxy, WebSocket Proxy, admin CLI, I mean, almost in all the components of the Pulsar ecosystem. Encrypting data in the transit, in between broker and application, that actually mitigates the risk for, unintended interception of data across the network. But as we know, it cannot protect the data which is stored in the media itself. So to satisfy the requirement, where Pulsar provides the envelope encryption. So encryption of the data stored on the storage media is used to protect the data from any unauthorized access if the storage media itself is stolen. Most of the encryption at the rest that uses symmetric key algorithm. So the data can be very quickly encrypted and decrypted. We don't want asymmetric key encryption because that can actually slow down the system performance. However, since the symmetric data key itself needs to be protected, we use the envelope encryption to secure the symmetric key, which actually makes very difficult for any attackers to compromise the data key. So what is the envelope encryption? Envelope encryption is the process of encrypting a data key with another key. So Pulsar provides some methods that allows us to encrypt message content on the producer side before sending to the broker. This message data will remain encrypted until a consumer with the correct private key consumes it and decrypts it and delivers to the application. So now let's look at how Pulsar client library encrypts and decrypts the message data. For that, first, Pulsar client library dynamically generates a symmetric data key in the process for the encryption, rather asymmetric key because of the faster data encryption which we need. Producer client library then encrypts the data key with asymmetric public key and then publishes encrypted message along with the encrypted data key. When consumer client library receives the encrypted message along with encrypted data key, consumer first uses its own private key to decrypt and retrieves the original data key. After that, consumer client library decrypts the actual message using the data key and then finally delivers the decrypted message to the application. In this entire mechanism, producer can also use multiple public keys for the encryption in case if there are multiple subscriptions of the topics and with different private keys exist. Also, to provide additional security if the data key itself is compromised, Pulsar client library also performs data key rotation at the configured time, to secure the data in case if the data key itself is kind of compromised. So envelope encryption and the data encryption, that enables our users in Yahoo to publish and persist data securely both on-prem and from the public cloud. However, when we talk about public cloud, one of the challenges we had to access on-prem Pulsar cluster from the public cloud was our on-prem cluster that they do not have any public IP address. So we need a gateway with a public IP address which connects the application deployed in public cloud to the on-prem brokers. And to deal with this security issue, we use Pulsar Proxy. Pulsar Proxy is a lightweight gateway which works on Pulsar binary protocol, and it can be used when direct connections between client and the Pulsar brokers are not feasible. For example, if brokers are running on containers and their public IP are not resolvable, right, for the clients, then we can run Pulsar Proxy in between client and broker. So in that case, Pulsar Proxy is the only component which has direct access to the broker, and it's sitting in front of brokers to create a channel between client and the broker. Aside from traffic forwarding, Pulsar Proxy provides security, by hiding the actual IP address of the server. Pulsar Proxy Server also performs authentication when client connects to the proxy, and then Proxy Server forwards client's principal name after it has authenticated client's request to the broker, so broker can later authorize the entire request when it actually creates proxy connection between client and the broker. So Pulsar Proxy provides accessibility and the security when the client cannot directly interact with the brokers. It is relatively very straightforward to deploy Pulsar Proxy by just providing broker service URL into the proxy configuration file, and Proxy also provides API to set up monitoring for the proxy traffic. So Pulsar Proxy provide us an opportunity to deploy Pulsar in containers and allows our user to access on-prem Pulsar from the public cloud. However, we have another use case where we need cross-enterprise or cross-organization messaging bus integration. Such cross-organization integration requires really higher security clearance because of the nature of confidential data flowing across two different independent organizations. To satisfy such requirement, we need an enterprise-grade proxy solution, which should forward client certificates as it is to the broker without terminating the TLS connection at the proxy. Also, the organizational policies often requires a system to stay behind enterprise grade proxy gateway servers such as HAProxy, ATS, Nginx, and after that it requires to follow the standard security regulations to protect system against the known vulnerabilities. So for such use cases, we need a messaging bus that supports enterprise-grade proxy solutions such as ATS or HAProxy. So for this use case, we have added SNI routing support into Pulsar, which actually enables us to access Pulsar via enterprise proxy solutions. Right now, Pulsar is the only messaging system in the market that actually supports enterprise proxy solutions such as ATS or HAProxy using the SNI routing. So what is SNI routing? SNI routing is a layer 4 TCP routing protocol that allows ATS or any other proxy to create a TLS tunnel between client and server and then move the data between two endpoints without modifying the data. One of the key functional difference between Pulsar Proxy and the SNI Proxy is SNI Proxy does not terminate client connection and forward the client certificate as it is to the broker when it creates a TLS tunnel between client and broker. So broker can authenticate and validate the actual client certificate. If SNI routing is enabled, then in initial TLS handshake, proxy server examines and extracts the hostname from the SNI header and forward request to that SNI host by creating a TLS tunnel between client and that SNI host. So when client sends a target broker address, let's say, as a part of SNI header during connection creation with proxy, then proxy will extract the target broker address from the SNI header and creates a TLS tunnel between client and the broker. So data can flow between client and broker securely. Pulsar client library supports SNI proxy, and it can be simply used by configuring SNI proxy URL of the proxy server. In the below section of this slide, it shows that how to configure SNI proxy at the client side. We need to provide proxy server URL and type of proxy, and which is SNI in this case, along with all the TLS configuration parameter. So we need to note here, SNI routing only works over the TLS. With this, all the proxy configuration, Pulsar client library will try to connect to the proxy server and pass its broker name as a SNI header. And proxy server will be able to after that extract the target broker name from the SNI header and will eventually create a TLS tunnel between client and broker. So this slide shows that Pulsar client can connect to the broker using SNI proxy. So we can also use SNI proxy for the geo-replication to replicate data between two brokers. So we can use such SNI proxy solutions like ATS or HAProxy servers as a forward and reverse proxy on both the sides of the client and server. Therefore, we can use proxy server for the geo-replication to enable geo-replication across two different organizations. The slide shows geo-replication between two different Pulsar instances running on two different organizations. This example shows that we have organization A at the left side, which has proxy server A deployed, and similar way we have organization B at the right side, which has proxy server B deployed. Now each cluster should know about other cluster for the discovery, and for that we have to update the cluster metadata in each region. Therefore, in organization A, we will add a cluster metadata for organization B with org B's broker URL and SNI proxy service URL. And in the same way, we'll add cluster metadata of organization A with SNI proxy URL in organization B's Pulsar instance. So when brokers at organization A wants to create outbound connection to organization B broker, it connects them to via proxy server using SNI routing and vice versa for brokers at organization B creates outbound connections to organization A brokers via proxy servers. So Apache Pulsar allows us to, it allows like two different enterprise or two independent different organizations to create a super secure channel in both the direction using enterprise level or enterprise grade proxy solutions. This is one of the major breakthrough we achieved using Pulsar, because right now none of the messaging system in the market except Pulsar that provides support for the enterprise proxy server such as HAProxy or ATS or any other proxy, which can actually link to different streams from the two different independent organizations together. If you need more information about SNI Proxy, you can always check out the tip 60 in the Pulsar wiki. And about the future work regarding multi-tenancy in Yahoo, we'll be working on tenant-based broker virtualizations, where we can have tenant-specific broker containers on a top of centralized bookkeeper service, which gives elasticity when tenant needs a higher fan in, fan out based on their own peak traffic. We'll be also working on hybrid cloud geo-replication solution, where independent Pulsar cluster on different cloud provider can perform geo-replication seamlessly. By saying that, now I would like to open the floor for any questions if anybody has.